Dr. David Fowler from the University of Texas in Austin. And Dr. Fowler today is going to talk on the design and behavior of thermal stresses and polymer concrete overlays.
I'll raise this up here. Switch. Oh yeah, okay.
They got a mouse there.
Yep. And the effect of age and cycling and the effect of shrinkage. And then I want to go through an example problem, and then we'll have a few conclusions. Failures have been known to occur in repairs due to thermal changes. It's particularly true for repair materials with significantly higher coefficients of thermal expansion. And failures are generally associated with the lamination near the edges of repairs. Let's look at a rather simple example here. If we have a concrete slab in yellow and a green overlay, if there is no temperature change, there is no stress between the overlay and the concrete slab. However, if we have a change in temperature, let's assume we have a temperature decrease. And for the moment, let's assume there is no bond between the overlay in green and the concrete slab. I think you can see that in most cases, since the polymer concrete would have a higher coefficient of thermal expansion than the concrete slab, then the change in length would be greater. And so if you look at the green slab there, you'll notice that the change in dimension is greater than it is for the yellow concrete slab, because again reflecting the fact that the coefficients of thermal expansion are normally higher. And we find they're anywhere from about 50% to maybe 200% higher, 250% higher than concrete. Now, obviously, we don't want that situation. We want the polymer concrete to be bonded to the Portland cement concrete. So what happens if we bond the polymer concrete to the Portland cement concrete and we get a temperature change? The green, the polymer concrete, wants to contract more. It can't because it's bonded, so it has some resistance, and it sets up, or there's a condition of shear stress set up between the polymer concrete and the Portland cement concrete. You'll notice down at the very end we show some arrows that are going vertically. What happens as that top overlay tries to contract and it can't, it tries to curl up at the same time, and so normal stresses, in this case tensile stresses, occur. You're going to see later these usually occur near an edge or a boundary. And so those two combinations of stresses, in addition to the axial stress, you'll notice in the green at the far end, axial stresses occur. So really there are three kinds of stresses. Axial stresses, we have the shear stresses at the interface, and then the normal stresses that usually are tension when you have a temperature decrease. And those are the stresses that we have concerns with because they may cause cracking or cause delamination between the polymer concrete overlay and the Portland cement concrete overlay. And what happens is the contractor's worst nightmare. In this case, a bonding agent or a primer was used, and because it was able to run down the slope of the bridge, it built up to a fairly large thickness, and later on when temperature changes occurred, stresses and then delamination resulted from that effect. And that's something you never want to see on a bridge deck. Several years ago, we decided to try to go through and do an analytical solution. We had some, I think, kind of some intuitive reactions to all of this. We felt like if we could keep a material that had a fairly low modulus as our overlay, it would work much better. But we didn't really know how to calculate the stresses. So we went through and tried to calculate the stresses. And I'm not going to go through all of the analytical solution. We went through and looked at some solutions that had been done in the past. We tried to modify them. And so we came up with a solution that we felt like was pretty reasonable. It was a rational solution. We neglected that adhesive layer between the overlay and the concrete slab. But we did assume that the composite beam is subjected to a uniform temperature change, which isn't quite right. We assumed that both the overlay and the concrete are at the same temperature. And we assume that the difference in the coefficient of thermal expansions tend to remain pretty constant throughout the temperature change. That isn't always quite correct. It's a fairly complex solution involved some differential equations, and once you get out of college you kind of forget how to do differential equations, so we had to go back and relook at some of that mathematics. But we tried to summarize this with some fairly easy to read graphs. This simply shows you that if you look at the stresses in a beam that has an overlay, that these stresses tend to occur fairly near the edge or the boundary. That boundary could be the edge of an overlay, the edge of a slab. It could be if you had a crack that goes all the way through the overlay and the slab. That could be the condition. Let me go on to the next slide. This really is, I think, kind of summarizes one of the main points we want to make. If this represents the depth of the slab or the beam, maybe it's about 8 inches in this case. I think we show about 8.5 inches, 8-inch slab and maybe a 1/2-inch overlay. You'll notice that these are interface shear stresses in white. The blue represent the normal stresses. The important thing to note is that these stresses are the highest magnitude right near the edge of the slab. They tend to dampen down to 0 by the time you get out about 8 or 9 inches from that edge or that boundary. And I think that's the reason why we always see the delamination beginning right at an edge or the boundary. They normally don't start out in the middle of the overlay unless maybe we have a poor surface preparation. But they start right near the edge and they can get to be fairly high. For this particular example, you'll notice that the normal stresses get to be about 70 psi and the shear stresses are about 130 or 140. Now in general, for that condition, I think we would expect the overlay to be able to absorb those kind of stresses. This shows the effect of changing the thickness of the overlay. This is a ratio of thickness of the overlay to the thickness of the slab. This is a pretty thin overlay. This would be a matter of a few millimeters in thickness, going all the way up to about 0.09. So for a 6-inch slab, that'd be roughly a 1/2-inch thick overlay. But again, notice that as the thickness increases, the red is for the thinner thickness, the white is the larger thickness. Notice is that the thickness increases, the stresses increase in the overlay. And that's something I kind of intuitively, I think we knew, but it certainly helped to see that mathematically. So that tells you that going to a real thick overlay probably isn't the way to go. Use the minimum thickness overlay that you can get by with, and you'll end up with less stress in the system. If we look at the effect of, and by the way, that previous one was on, let's see if we can go back, that was on, that was for interface shear stresses. If we go to the next one, which is the normal stress, we see a somewhat similar effect. Here the stress is not quite as large, but they're up around, say, 80 psi. But again, notice, this is the thinner overlay, next, and then the thickest overlay. Again, we see these stresses dampening out about 7 or 8 inches from the edge of the overlay or from a crack that goes all the way through. If we look at the effect of modulus elasticity, again, I think intuitively we've known that we ought to go to a material that has a lower modulus. And I remember way back 15 years ago or so, and when Mike Sprinkle and others were working, we kind of intuitively knew that we ought to keep a material that has a high elongation. It would be associated with a lower modulus. Well, again, you can see that if we have a modulus of about 0.025, this is the ratio. So that's pretty low. This is around maybe 100 or 150,000 psi. And that compares now with a modulus ratio of 0.5. That would be at maybe around 2 million. And so again, you can see that the lower modulus material is going to have a much lower stress, this is for shear, than the higher modulus material. And again, if we go to normal stresses, we see the same kind of effect. Higher stresses for the higher modulus material. What we reduced all of this down to was a set of curves. This could all be done on the computer, but it can also be done by hand. This shows the interface axial stresses. We had to select a value of strain that we could use to produce this. And this value of strain represents the temperature change times the difference in coefficient of thermal expansion between the concrete and the polymer concrete. So that's pretty simple. We set that at 500. Now normally when you do the calculations, you'll see later it never is quite 500, but you can always ratio it out. And so it's easy to use these curves and come up with the stresses that apply to your particular case. But notice on the bottom, this shows the thickness ratio. These values are the ratio of modulus of elasticity between the overlay and the concrete. And this will give us then a stress. This happens to be the one for axial stress. This is the one for interface shear stress. Again, you can see that in this case, as the thickness increases the overlay, the stresses go up. This shows an increase for the modulus of elasticity. And then we go to normal stresses. Again, the thickness ratio and the ratio of modulus. Can't quite explain why this happens. For these higher values of modulus ratio, the stresses kind of reduce. That's all the mathematics. I think it's correct, but I can't really explain that why that happens. We went back and looked at some strain gauge data that we had from an overlay. This was an overlay that was kind of thick because it's kind of hard to measure strains in real thin overlays. This was a 2-inch overlay and a 5-inch slab. We went through and measured the stresses by strain gauges and then compared that with the analysis, and we found that we really got pretty good results. So we felt pretty good about the comparison between the theoretical and the predicted and the actual values. One of the things that comes up sometimes is relaxation. We know that polymers relax due to creep. And so there's not a lot of good data out there for that, but we did find a reference in the literature. And this is a fairly long, involved equation here for the modulus of elasticity as a function of time. It gives you really the relaxation modulus for a t and time in hours. Well, that doesn't do you a lot of good, but I'll show you in a minute how we can go back and simplify that down. We compared that with some of the experimental data we had. We found that it gave us pretty good results. In 5 hours, we found that we had about a 21% difference. For 8 days, only about 11% difference. So again, we felt like it was that particular equation gave a pretty good prediction for relaxation. And so what we decided to do then was try to look at the kind of extreme case. If you look at time being infinite over time being t equal to 0, using that ratio, it was a value of about 0.7. And so we felt like using a conservative value of about 0.7 would be appropriate. So what we would say is, for the worst case, you'd find a relaxation of about 0.7 for your modulus of elasticity. What about the effect of age in thermal cycling? Well, it's pretty well known that as these materials age, as polymer concretes age, and you increase the number of thermal cycles, that you generally tend to reduce bond strength. And I'm indebted to some of Mike's data, Mike Sprinkle's data, that he took over the years. I went back and just plotted some of these up. I probably will go through some of these fairly quickly, but Mike found, and these all came from some of his bridges in Virginia, where he would go out and measure bond strength or shear strength. He'd take these over a period of years, and he almost always found there was a reduction in strength. I think the one in the dark color here was MMA, had about a 2% elongation. I believe this was a polystyrene material that had about an 8% elongation. This was the measurement of the elongation of the neat resin. Again, this was I believe that was an epoxy, Mike. I can't remember. It had a large elongation, 30%. And again, this particular one happened to have a pretty good decrease in tensile bond strength. Generally, I think he found that when they had high elongations, that drop-off wasn't nearly as great. But almost always, he found over a period of 4 or 5 years that there was a reduction in bond strength. And I'll simply flip through some of these fairly quickly. This is one in which he measured shear bond strength, both as a function of number of cycles and years, and again, a pretty good drop-off in strength. Go and flip through this fairly quickly, but everyone who's measured bond strength with time has almost always found there is a reduction in bond strength between the overlay and the concrete. Then the question that always comes up about shrinkage. Shrinkage strains produce the same effects as thermal contractions. Now, shrinkage is relatively short term, particularly for polymer concrete. We know that generally shrinkage occurs over a matter of a few hours or a few days. For Portland cement concrete, it may occur over months or maybe even many months. But the question was, how does relaxation affect shrinkage? Well, we developed a test a few years ago, and I think some of you may have even seen this test before, but in this case, we take a Portland cement concrete slab, And we place a bond breaker right in the center, and then we place down our polymer concrete overlay. Into that we put some electronic transducers so we can eventually measure what that change in length is. And after certain periods of curing time, we come in and make a cut right here. Oops. We make a cut right there. And then we measure to see what kind of rebound, what kind of shrinkage we get. And we find that, let me go and pass on through that written stuff, but we find that if we compare that with the unrestrained, if there's no restraint, so you put it in a box and measure the shrinkage, the shrinkage was quite high, up around 700 or 800 microstrains. If we allow that beam to cure for 7 hours and then cut it right here, we find that we would get about maybe 250, close to 300 microstrain. If we wait 2 more hours on another specimen, 9 hours, you'll see there's less shrinkage. If we waited 3 days, there was no rebound, which indicates that relaxation had occurred completely. There was no shrinkage in that overlay. So that told us that the shrinkage was pretty well absorbed in a period of a matter of a few days. This happened to be an epoxy polymer. Generally, epoxies don't shrink as much as some of the other materials. But from those results, we decided that it was pretty clear that relaxation causes a pretty rapid decrease in the stresses due to shrinkage. And so it appears that we can neglect shrinkage stresses except in the first few hours, maybe for a very short-term scenario. Well, then we want to go through an example with you to show you how we could use some of these results. And in this case, we're going to look at some short-term effects and some long-term effects. We have an overlay that we're going to assume it's a 1/2 inch thick and a Portland cement concrete slab that's 6 inches thick. The coefficient of thermal expansion we'll assume is about 5.5 times 10 to the 6 for the concrete. It's a pretty normal value. And for the polymer concrete, we're going to assume there's a slight variation, which is a function of a temperature. 13, 12.5, and 11.5. These are actually measured values. I think maybe I've got, yeah, there you have a curve here that we used in the laboratory. We found in the laboratory. And many of you know that polymer concrete exhibits somewhat of a bilinear coefficient of thermal expansion relationship, somewhere up around 80 to 100 degrees. Most of these materials will tend to have a higher slope on that curve. It's somewhere up around the term escapes me now, but it's about the point of what's the word I'm trying to think of? Well, let's pass on. Yeah, the softening point. There's another. Yeah, T sub G. Thank you. I was blank. The other properties, and again, these are for some test results. Poisson's ratio about 0.24. Modulus elasticity, again for the polymer concrete, again it varies with time and also with temperature. So we assumed about 2.50 at 75 degrees after 16 hours. At 85 degrees, about 3 million, and 4.5 million at 40 degrees. Now this is a high value. These are much higher than you normally want to use. We picked some high values, but normally you'd want to use a modulus that was considerably lower than this. And again, looking at flexural strength at 16 hours, about 2,300 long term. At 40 degrees, drops down about, or increases to about 4,000. Then look at the shear bond strength at 0 cycles and 160 thermal cycles. This was found in the laboratory by cycling these materials and then doing the shear bond strength. Tensile bond strength about 350 and 300 after 160 cycles. We looked at 2 different scenarios for time. We looked at a very short-term effect where the deck surface would reach about 100 degrees Fahrenheit during the day and drops to 50 degrees overnight during a 16-hour period. Then we looked at another scenario, a long-term seasonal change, where it would drop from maybe an average of 100 degrees, maybe this is in Texas, down to 70 degrees. Then in addition, superimposed on that, we would assume that a cold front moves in and drops the temperature over a very short time from about 70 degrees down to 10 degrees Fahrenheit. And the thermally induced strain, looking first of all at the short-term analysis, it's pretty easy to calculate if you remember your physics. You take the change in temperature, times the difference in coefficient of thermal expansion. Now, in that short-term analysis, you may remember we were going from, let's go back a couple of slides just to refresh your memory. We're going to go from 100 degrees down to 50 degrees. So the average temperature is going to be 75 degrees during that time period. So we will use that average of 75 degrees. From that, we will get our coefficient of thermal expansion for our polymer concrete, and that would be the 12.5. Concrete is a constant 5.5 for all temperature ranges. We take that difference times the difference in temperature, 100 degrees down to 50 degrees. That gives us our strain, if you will, for that condition, 350 microstrain. Then to go to those curves that we'd shown earlier, we need the ratios of thickness and the ratio of modulus of elasticity. The ratio of thickness turns out to be a 1/2 inch over 6 inches, or 0.083. The modulus of elasticity ratio is about 0.6. So we go to the curve, and I'm not going to take you through all of these because it gets kind of boring, but if we look at the axial stress, using our thickness ratio, going up to our modulus ratio of 0.625, we find that value is 1,360. Again, remember that that's for this strain condition, arbitrary strain condition of 500 microinches. We do that for all the other conditions. Let's not worry about all the numbers, but we come up with these three values of stress. That's from the graph that used the 500 microinches per inch of strain. Now we have to correct those. One of the corrections now is from the fact that we don't have 500 microinches, we only have 350. So we simply take the ratio of 350 over 500 and use that as a multiplier. The other correction is that we have a slab rather than a beam. All of these values we found and the curves were for beams, so we have to multiply that by 1 over 1 minus Poisson's ratio, and so that gives us a multiplier of 1.32. So if you haven't gone to sleep yet on me, then we take the stresses we got from the curves, multiply it by the two multipliers. This is to correct it to a slab stress. This is to correct it from 500 microstrain back to a 350 microstrain. This gives us then the stresses for the short-term conditions. We go through and do the same thing for the long-term analysis. And we find that for the seasonal change, 100 degrees down to 70 degrees, we have a strain of about 225 microinches. We have the same ratios of thickness and modulus that we had before. So we'll have to correct from the 500 microstrain. The multipliers again would be the one for slab action, because we're using a slab rather than the beam. Then we're going to relax it. We're going to, over this long period from winter to summer, or summer to winter, we're going to relax it by 0.7. We're going to see the modulus of elasticity changes by a factor of 0.7. And then of course we have to convert our strains from 225 to 225 from 500 rather. And that's a ratio of 0.45. After we go through and make all the corrections, these are the stresses for our seasonal changes: 560, 121, and 50 for the three stresses. We go back and do the same thing then when that cold front moves through. This is a short-term condition. It's not a condition where we'd have to consider relaxation. We drop from 70 degrees to 10 degrees, and we have an average temperature of 40 degrees over that change. So again, we go back and find what our strain is, go to our curves, and we come up then with our final stresses. So in effect, what we want to do is to superimpose the cold front stresses on this seasonal change. And let's go to the long-term stresses. We get the seasonal change of 565 psi plus 1292, so the total stress, the axial stress, will be about 1800 psi. The shear stress turns out to be about 400, and the normal stress is about 164. Looking at the big summary table, and we're just about at the end of this, we found that for short term, the stress was about 1257 psi. The long term was about 1857. We've got two different allowable stresses. The ultimate stress over the short term would be about 2300, but over the long term, about 4000. In both cases, we're okay. Our ultimate stress is greater than the allowable. Same thing for shear. 268 versus 1500, and 397 versus about 1000. So in this case, all of our stresses turned out to be within the ultimate stress, and so we wouldn't predict a failure. Some of the coefficient of thermal expansion in this case was probably fairly typical. I think for this polymer concrete, I think the modulus of elasticity is a little bit higher than I would like to see. But based on the calculations, both the short-term and the long-term stresses are within the allowable. If the stresses were excessive, then the thing to do probably be to use either a thinner overlay and or a lower modulus. And generally I would want to use a lower modulus than the one we use. We simply were using an example of some polymer concretes that we had tested in the laboratory. What else is needed? Well, first of all, we need some very accurate material properties in order to use this method. We also need to have a better idea of what the design changes in temperature should be. That's very critical to making the calculation. We need to have a better idea of what that relaxation is for these materials. We found that one curve for epoxies, but for other materials, I'm not really sure what we should be using. We ought to verify the method with test results. And then eventually, if this proves to be an acceptable method, we ought to incorporate the methodology into the design of repairs and our specifications. The same method would apply whether it be a repair or whether it be a large overlay. As long as you're putting down one material over another and you have differences in thermal coefficients, then you could use this procedure. But I think it's clear that stresses due to thermal changes can be very significant in placing two materials together in which the coefficients of thermal expansion are different. But I think it is possible to predict what these stresses are using rational procedures. But I think we also need to have some additional research to validate the method. Be glad to answer any questions. Yes, Mike?
What was the modulus again of that material that you tested used for your example?
It varied. It was up between 2 and 3 million. It varied with temperature, as you know. There's a difference in modulus, but it's up right in the range of 2 to 3 million. So it was fairly high modulus material, which, again, normally you wouldn't want to use a material that high. For this example, it turned out that the stresses were okay, but I think there might be some other cases where it wouldn't be. One thing that helps is we used a pretty thin overlay. And I think we used to have the feeling that intuitively you didn't want to get a real thick overlay, but this analysis really shows that the thicker the overlay, the higher the stresses are going to be. Yes?
Do you think that this method would correlate to the ASTM test for overlays on concrete, that cycling test where they put on a concrete block and different thicknesses, and just cycle it, freeze it off?
Well, if you remember what we used here, we used some results, some experimental results for cycling overlays. So I don't think this is probably going to take into effect cycling. In fact, you need to know what that change in bond strength is between the overlay and the concrete to use this method. That gives you your ultimate stress, if you will. So that really wouldn't take into effect cycling. All it does is take into account the effect of temperature on the stresses that are produced. But the cycling is known to decrease the long-term bond strength, and somehow you'd have to get that. Right now, the only way I know how to get that is by experimental results, experimental test. Yes?
Early in your presentation, you showed the highest normal and shear stresses at the edge of the member and went down to 0 within about 8 inches.
Yes, yes.
Was that due to your model simulating cracking, or did the stresses just relax at that point, or why would they go to 0 so quickly?
That's what the mathematics tell you. The key is the high stresses are right near the boundary. And again, that boundary would be an edge of a slab, or I think the same thing would hurt if you had a crack all the way through the slab. That's the reason why it's very important, I think, keep cracks out of through cracks. Cracks that go all the way through the overlay and the slab, because that's another potential stress riser at that point. I'm not sure I can tell you why it dampens out so quickly. That's what the numbers give us. It's pretty hard to go through, and since this comes from pretty complex mathematics, I can't go through and visualize what's happening there as far as the mathematics are concerned. I think intuitively, though, I think you'd expect it to dampen out pretty quickly from the edge. Yeah, Mike?
I don't have a question, it's just a comment. First, obviously, it's very useful information. years, I've been involved with a number of polymer overlay failures, and in all of these failures, the products that failed have a very good track record. But in the situation where they failed, the material had been placed at a much greater thickness than the usual application.
Right.
For example, normally lay down a quarter of an inch and perform well for 20 years. In this case, for whatever reason, they put it down a half inch, 3/4 inch, and the product failed. And your data there obviously shows why it occurs. The risk of failure increases as the thickness increases.
Right, right. I think I think you can almost kind of logically determine why that's true. You're going to get a certain strain in that material, and strain times modulus gives you stress. And the thicker it is, you're going to get more. The more stress you have, times a greater thickness is going to give you a greater force. And as that shearing force occurs, as that material tries to shear off the surface, move the surface, the thicker it is, the larger the force, the greater that shear has to be there to resist it. So I think it's kind of logical that you want to keep it thin. So thicker isn't always better. We get that. Well, if a quarter inch is good, an inch would be great. That's in this case, it's not true. You want it just thick enough to take care of your wear and other conditions, and then cut it off. It's the worst thing you can do is make it thick. Yes.
Can you preempt these any failure or maintain safety precautions just by tapering the thickness as you get closer to the edge of the building?
Yeah, that's come up before. I think you probably can, Dan. We have the mathematics get a lot more complicated when you start varying the thickness of it, obviously, and we haven't tried to do that. But I think that would help. I think it would help, obviously, if you could make it thinner near the edge. And you can see that effect is pretty short range. So over, say, the last 7 or 8 inches, if you could taper it down, I think it probably would help. I don't know, Mike, have you ever tried that?
We've never tried that.
Yeah.
I mean, based on what you're reporting there, it should help.
Yeah, we thought about that, but we haven't tried to go through and do anything more. Just think about it. If you got some research money, we'd love to look at it, though. Yes.
A question to what I had before. Would you say that you could test something like that with lab size material, like say a 12 by 12 slab, and varying thicknesses, and maybe putting it in different chambers? Or do you think the size of the sample would be
I think it ought to be more than 12 inches by 12 inches, but you could certainly test it on, I don't know, maybe 4 feet by 4 feet or something like that. You could even test it on a beam, probably. In fact, it's kind of interesting. And I wish I'd brought along a picture of the slide of it, but on that shrinkage specimen you saw up there, one of my students came in to see if he could knock off the material, and when he knocked it off, it's kind of interesting that the failure was right around the edges where you can tell where the high stresses occurred, right around the edge of the boundary. But you'd prefer to have a slab a little bit larger, maybe 4 feet by 4 feet, and you could keep the slab fairly thin so that you could get that edge effect fairly close to the boundary. But maybe at some future time we could even think about putting something like this into one of our design guides as kind of at least an indicator of what the stresses are. Might be of use. That's it.
Thank you, David.